Welcome, Eliav. The floor is yours.
Thank you, Ofer. My name is Eliav Shtull-Trauring. I work in Dr. Nerit Berenstein's lab in the Institute of Soil and Water Environmental Sciences. Today I'm going to be speaking about our research about treated wastewater irrigation, and specifically towards sustainable treated wastewater irrigation, salinity and nutrient content trends in Israel. So the talk structure: first, I'll give a very short introduction about treated wastewater, challenges and potential. Next, we'll discuss trends in salinity, the impact of large-scale desalination for drinking water and treated wastewater. Next, we'll talk about trends in nutrient content, specifically NPK, and in their environmental and nutritional sustainability. Then we'll have a short recap of these two issues, and we'll see the lesson learned from these two sections and what we can do to get closer to sustainable treated wastewater irrigation. And then if we will have time, I will present a related project, which is called the Interactive Agri Atlas. So let's get right into it. Treated wastewater, challenges and potential. And this is the big question: is how do we turn wastewater, which is basically the water coming out of our sewage, from waste into a resource? And this small statistic, where 80% of the global wastewater is released to the environment without adequate treatment. So we see that's already a big challenge. And like we said, this is the first challenge, is the challenge of collection. So this is data from 2011. And we see even in countries like the United States, we only reach between 60 to 80% collection. In places like China, 30 to 60%. But we see another big problem is the no data available. This is in the world, a lot of times the data is just not there. And basically when we're not collecting it, it means that this goes usually straight to streams. Another challenge is the removal effectivity, and this is dependent on the quality of the treatment. And the problem is that there's different elements that you need to remove. We have salts, which are usually not removed by conventional plants, nutrients, organic matter and suspended solids, microbial pollution, heavy metals, and emerging contaminants like pharmaceuticals. But we're going to focus on these two first. The salts and the nutrients. So we saw the challenges, but there's also the potential, and there's many different potential, but we're going to focus on the reuse for irrigation in agriculture. That's going to be the focus of this talk. So a small slide about treated wastewater in Israel. According to the OECD, 99% of the sewage is collected. Out of that, 97% is treated. And from the 97% treated, around 85% is used for irrigation, which as this is, Israel is the leading country in the world when it comes to reuse of treated wastewater. So there is a lot to learn from Israel, and this is what our study came to do. And we'll start with the first part, which is the trend in salinity, the impact of large-scale desalination for drinking water. This was published a month ago in a study with Manny Ben-Hur and Yossi Tanai from the Institute and Ariel Cohen from Nature and Parks Authority. And just the bottom line before we get into the details. So first of all, we see that large-scale drinking water desalination significantly reduced treated wastewater salinity. And this was expected in many ways, but the second thing we saw, which is a bit more dramatic, is that treated wastewater with desalinated base water can remediate groundwater salinity. And we'll see this in fuller detail as we go. So a little background on the water use trends in Israel. So here in the graph, we see on the x-axis the years. Here on the top, we see the national water consumption in million cubic meters by different types of water. And in the bottom, we see the agricultural water consumption by type. And we see here two major trends. Sorry, if we look at the national water consumption, we see a very dramatic reduction in the fresh water from 1998. And from 2006, we basically see the desalination filled in the gap of the reduction of the fresh water. And the second thing, if we look at agriculture, then again, we see this reduction in freshwater use and the increase of treated wastewater. Here it's divided into treated wastewater and the Shafdan soil aquifer treatment. And we see the increase over the years. Okay, so what did we do? What's the methodology of this study? So first of all, what we did is we took water quality samples from over 80 treated wastewater plants. These are in the green dots from 2000 to 2016. This is part of a monitoring program of the Nature and Parks Authority for the Water Authority. And we also take water quality data from 1990 to 2016 from the Shafdan soil aquifer treatment plant, which what this soil aquifer treatment means is after the biological treatment, there's another process of filtration through sand, basically into the aquifer, and a residence time of 1 year, and then after that it's reused for agriculture in the southern area. So we see in the dark purple are the areas irrigated with a Shafdan, and in the pink are the agricultural fields irrigated with other treated wastewater. So what we did, we looked at the concentrations of chloride, sodium, magnesium, calcium, boron, SAR, and electroconductivity. And first we compared 3 treated wastewater plants which receive mostly desalinated base water, which is Shafdan, Ashdod, and Beersheba, and 3 treated wastewater plants which receive mostly freshwater base water, which is Carmel, Solelim, and Tiberias. The second thing we did is we compared, instead of just selected plants, all the plants in the Kinneret, which receives mostly freshwater, and all the plants in the coastal area, which receive mostly desalinated base water. And finally, we analyzed the pre and post soil aquifer treatment concentrations in the Shafdan. So let's dive right into the results. So we'll start with the results for the selected plants for chloride and sodium. And again, in the graph, we see here on the x-axis the sampling period time, so either in days from the first sample or in years. And on the y-axis, we see the concentration of chloride on the top and sodium on the bottom. And the left side are the 3 plants which received desalination water, and on the right, the ones that received non-desalination water. And like as we see, oh, and one last thing is we drew the trend line if there was P less than 0.05. So that's when we saw a trend, that's when we see the trend line is drawn with a 95% confidence interval. So as we see, there's a very clear decrease in the chloride concentration in the desalination plants, with the Ashdod showing the most significant decrease. We see a same trends with sodium, while in the non-desalination source, we do not see any trends except a small increase perhaps in the Carmiel plant.
ליאב, אני צריכה שאני מצרה, אנחנו לא רואים את העכבר שלך.
לא רואים את העכבר?
לא.
אוקיי, סליחה. עכשיו רואים?
עכשיו רואים.
Okay, so like I said, we see a decrease in the desalination on the left, while on the non-desalination plants, we do not see a decrease and perhaps even a small increase in Carmiel. Next, we look at it's the same graph structure as we saw before, just for calcium and magnesium. And again, we see decrease in all the desalination source plants for calcium, and even a much more dramatic decrease for magnesium approaching 0, while the non-desalination source, we do not see any trends. Here we see SAR and boron on the bottom. So SAR, we did not see any clear trends. Perhaps there was a small decrease in the Ashdod plant. We see with a very large confidence interval, but on the non-desalination source, we did not see any trend. And if we look for the boron, while we didn't see for all plants trend, we did see an increased trend for Ashdod and the Shafdan plants, but we also saw a small increased trend also in the Carmiel plant. So this is a summary table of the changes in the different plants. And I just want to focus on the Ashdod plant. And we basically see the percentage of change for the different elements. And we see for chloride, we saw 70% decreased sodium, almost 60%. Magnesium, we saw a decrease of almost 90%, and boron, an increase of 50%. And this is maybe the upper limit of the change, but we see this is a very, very dramatic change in a 10-year period. So let me summarize just the results we saw just now. So first of all, we saw a decrease in chloride, sodium, calcium, and magnesium, and no change in SCR, and an increase in boron for plants receiving desalinated water. Next, we saw a varying rate of change, or the slope of the angle between the selected plants. And this is affected by a number of factors. First, the percent of the desalination base water. So different plants receive a different amount of desalinated base water, and this affects the rate of change. The second is the number and size of sources. So Ashdod receives most of its treated wastewater from the Ashdod municipality, while the Shafdan, which is a bigger plant, receives from many different municipalities, and also some places that receive fresh water, some places that receive desalinated water. So there's a much bigger mix. And the third factor is the concentration in the base fresh water before desalination introduction, which basically this means that, like we saw in the Ashdod, the initial chloride levels were much higher, so which leads to then to a much more significant decrease. Another thing we saw is the calcium decrease went down, but it was not as dramatic as magnesium. This is because the decrease is buffered by addition of calcium as part of the desalination process. And another very dramatic thing that we saw is that magnesium began approaching zero by 2016. We saw that SCR, despite fears that it might increase, remains unchanged, perhaps even a slight decrease. And we also saw an increase in boron approaching the 0.4 ppm threshold. And the source is probably sea boron, which has a lower filtration rate in the desalination compared to other materials, which causes an increase in the concentration. Okay, so next we saw the results for the 3 selected plants. Now we're going to see the same results, but for all the plants in the different aquifers. Like we said, the coastal on the left in the Kinneret. And again, we see on the x-axis is the time period, either in days from the first sample or years. And on the y-axis, we see the chloride over here, sodium over here. And here, in addition to the regression line, we drew a locally weighted regression, which shows the trend, which is not like in sodium, we see it much more. It's that the decrease didn't begin immediately at 2006. There was a small increase, and then the decrease started. But like we saw before, there's a decrease in chloride in the coastal and no trend in the Kinneret. Sodium also, the similar trend. Here we see the results for electrical conductivity. You see Again, we see an increase from around 2 to around 1.5. This is Siemens per meter. Here we see the results on the left for calcium, magnesium, SAR, and boron. And again, if we want to summarize, we see the results from the aquifer comparison confirm the same trends we saw in the selected plant analysis. In over 10 years, if we look at what's the percentage of decrease, we saw around a 20% decrease, and this is in the coastal aquifer area. We saw a 20% decrease in chloride and sodium, a 40% decrease in magnesium, and around 30% increase in boron. We also saw a small increase of boron in Sea of Galilee, which raises the question, perhaps there are additional sources except desalination. And next, we're going to talk about the results from the soil aquifer treatment plant. So this is results from the Shafdan. And what we see in this graph and following graphs is on the x-axis, we see the year, and it's starting from around 1988. And on the y-axis, we see the concentration. And what we see is on these full squares, this is the concentration pre-soil aquifer treatment, and the full circles are the concentration post-soil aquifer treatment. And this line is 2006 is when desalination started. So what we see here from around 1990 up to 2006 is a decrease from around 175 ppm approaching 250, with a very significant dilution from the pre and post-SAT concentration. But from the start of desalination, we see a very dramatic increase. And basically, we came back down by 2016 to levels similar in 1990, with almost no difference between the pre and post-SAT concentration, sometimes even higher. So basically, what we're seeing here is that there's a potential to remediate aquifer salinity with treated wastewater. And this is very interesting, we thought. Here we're going to go to the different more concentrations of sodium. Again, we see similar trend like in chloride, electrical conductivity, the same. Notice how the pre-SAT electrical conductivity is lower than the post-SAT. So there's the opposite effect of the dilution we saw before desalination. In calcium, we see also a similar trend with a significant dilution also after. But with magnesium, we start seeing that from around 2010, 2011, the post-soil aquifer treatment concentration are higher than the pre-SAT, which means there's some magnesium being added instead of being removed like we saw before. SAR, again, it's much more difficult to see a clear trend, even though it does look like there's a slight decrease. In boron, there was a very significant decrease before the soil aquifer treatment, and then a small increase in the pre-SAT levels, but the post-SAT levels remained pretty much unchanged. And this is not completely related to our first section, but I just wanted to show you the results for nitrogen and phosphorus, pre-SAT and post-SAT. And here again, we see that desalination didn't really have an effect on N or P, but we see again the significant reduction between the pre and post-SAT levels. So if we summarize what we saw in the soil aquifer treatment, we saw a significant reduction in salinity after desalination for chloride, sodium, and EC, and concentration reduced in 10 years what they increased in 20, which is very interesting. The magnesium concentrations pre-SAT are lower than post-SAT in the last years, which suggests this possible cation exchange processes with calcium when magnesium goes beneath a certain threshold. And this is similar to what Granot and Kurtzman saw when with using desalinated water. So we saw the same thing in the treated wastewater with desalinated base water. With boron, the large decrease we saw before desalination is possibly due to environmental regulations which limited boron use in detergents. But in the process we saw, which suggests that when the boron concentration was high, there was absorption to clay minerals, but when they were low, there was mobilization from the unsaturated zone to the treated wastewater. And the reduction we saw in the last few years is a possible absorption to organic matter and suspended solids in the infiltration ponds. And the results also raise the question, is soil aquifer treatment cost effective in considering the entrance of desalination? Because for at least the salinity, chloride, sodium, and EC, there's limited water quality improvement after we introduce desalination. So to conclude basically this whole chapter about reducing salinity with desalination. So first of all, we see that the drinking water desalination approach, which means desalinating water for drinking water, resulted in a dramatic reduction in the chloride, sodium, and EC in the treated wastewater irrigation. This has positive ramifications for agriculture, first of all, by reducing long-term damage to soil and crops from high salinity, and also reducing the irrigation requirements which are needed for the leaching of the salts. Another interesting conclusion is that the long-term soil aquifer treatment without desalination in the long term will lead to increased groundwater salinity. And the question whether this is sustainable in the long term or will it reach levels that are too high for agricultural irrigation. However, once desalination came into play, we see that the reduction of the groundwater salinity was so dramatic that it suggests that we could actually use treated wastewater for remediation of groundwater salinity. Negative impacts that we saw include a reduction in calcium, but more significantly a reduction in magnesium, which is also unhealthy for humans, but also unhealthy for crops and requires adding magnesium, which used to come in the water. We also saw increase in boron concentration in treated wastewater, which could cause a problem in the long term. We also saw that SAR did not increase despite fears that it would increase, and this is probably due to the concurrent reduction in sodium, magnesium, and calcium, which balance each other out. And another important point is the importance of the extensive and frequent monitoring of the treated wastewater and groundwater to support informed management and policy decisions. And we're able to understand all these trends because Israel has a very extensive monitoring program which allows us to analyze these trends, but this is not the case in all places. So this is the end of the salinity part. And unless there's pressing issues, I will move on to the second part of the talk, which is dealing with the nutrient content and in the treated wastewater and what we call environmental and nutritional sustainability. So like we said, these NPK, as we saw, are not affected by desalination, but there's, it was interesting to analyze it. And basically we came up with these two terms to analyze how to better irrigate treated wastewater. One is this idea of environmental sustainability, which means we want treated wastewater with low N and P to reach areas with high hydrological environmental sensitivity. And but the other part is the nutritional sustainability, which means we want treated wastewater with high NPK concentration to go to low hydrological and environmental sensitivity areas. and I will explain this more in detail. And I just want to say this is part of a article which is published and under review. Again, we did this with Manny Benchul from our institute, and Ariel Cohen and Matan Israeli from the Nature Parks Authority. Okay, so again, a general graph showing the national trends of treated wastewater irrigation. So what we see here again on the x-axis is the years, and we see the water use in million cubic meters. In the purple, this is the treated wastewater volume, which we see increased, and the blue empty circles are the freshwater volumes. We see the variability. And on this other axis, we see the irrigated area in 1,000 hectares of treated wastewater. So we see here a few interesting things. One of them is that from around 2009, the treated wastewater volume is higher than the freshwater volume, which means treated wastewater became the main irrigation source for agriculture in Israel. And another thing we see is that the stability in the supply of treated wastewater volume is much higher than the freshwater, which is driven by annual variability, which has to do with rainfall and the availability in the reservoirs and groundwater. If we divide the water used by the area, we reach around 400 cubic meters per dunam, which slightly decreased over time. But we have to remember that this includes also field crops and technical irrigation. So this might explain why it's a relatively low number. Okay, so next, just a general introduction about this idea of hydrological sensitivity. And on the left here, we see a map of Israel. And the three colors here are a division of Israel into three levels of hydrological sensitivity: low, medium, and high. And this is basically created by the Water Authority, and it's determined by many different factors like the soil, the groundwater, are there wells nearby, and all these different factors which determine which areas are more sensitive to irrigation with treated wastewater. And basically the high sensitivity means there's a greater risk to water resources. What we see here is also a map of aquifer basins, which is based on the Water Authority map, and with great help of Dr. Danny Kurtzman, we made a more detailed map. And on the right, we see the 6 selected aquifer basins for the study. And the different dots represent the location of the different treated wastewater fields by the crop type. So in this page, what we see here is on the left, it's the 6 different selected coastal aquifers, and the area, and the y-axis is the area of the fields in each one of the different sensitivities. And on the x-axis, we see the 5 years in which we did the study. And on the right side, we see the same idea, but instead of the total area, we see the percentage out of the total, with the multi-year average of the total area in each aquifer on the top. So we see basically a difference. While we have certain, certain aquifer basins which have a large percentage of the crops that are irrigated in low sensitivity areas, in places like the Sea of Galilee, we have a high percentage of the area in high sensitivity areas, and also in the coastal basins, which is high and medium areas. So there's a difference between the aquifer basins in their hydrological sensitivity. Here we see for the different aquifers, the different types of crops that were grown. And if Shafdan is irrigated there, we see the percent of the Shafdan. So like we see in the Western Negev, almost 85% of the water used there is Shafdan water. So like we said, we chose 6 aquifer basins. We chose 6 orchid crops: almond, avocado, banana, citrus, dates, and olives, and 5 years, which correspond to the years in which there's the biannual report of treated wastewater quality is published. So if in the first study we looked at the quality of the different treated wastewater plants, here we went into a more detailed level, and I'll try to explain because it's a bit complicated. So basically on the left, we see the location of all the wastewater treatment plants, which are in this square, and the reservoirs, which are in a circle. And what we basically did is we associated each field irrigated with treat water to a reservoir, and each reservoir was associated to a treatment plant. And the treated wastewater quality for each field was determined by the quality for the associated reservoir if we had details. If there was no information for the reservoir, we used the quality data for the treatment plant. And if also the associated treatment plant didn't have data, we used a regional average. And so in this way, we managed to get the quality of water irrigated in each field, and the volume of water was based on reports of farmers and and the amount of water they irrigated. And I'll just say in a side note that the water use is an overestimation of the total use, but it still gives us a good understanding picture of how the picture looks like. Okay, so this is basically the data we were using, but our methodology involved looking at 2 aspects. We looked at environmental and nutritional sustainability. So what is environmental sustainability? Environmental sustainability basically means we want to minimize the leaching of nitrogen and phosphorus to the environment. And how did we determine this? We took the concentration of the treated wastewater irrigation, divided it by the environmental standard, and we multiplied by 100. So basically we got the percentage above or below the environmental standard. And when we're saying if we're above 100%, this means you're not environmentally sustainable. And the Israeli environmental standard for irrigation with treated wastewater unrestricted is 25 ppm for nitrogen and 5 ppm for phosphorus. But the second aspect is the nutritional sustainability. And this basically means the maximizing the utilization of the nutrient content in the treated wastewater. And why this is important is because removing nutrients from treated wastewater also costs energy and money. Also the extraction of fertilizers contains things like mining, which also has environmental impact. And of course, it also can, any nutrient the farmer has to add, it's also additional cost. So we basically want to maximize the nutrient content that's already in the treated wastewater. So how do we calculate this? We took the nutrient content in the treated wastewater, this time in kilograms per hectare per year, which is basically the concentration times the value, and divided by the crop fertilizer recommendation. And again, multiplied by 100, giving us the percentage above or below the crop requirement. So in this case, 0% means that it's not nutritionally sustainable, which means the treated wastewater is not providing any of the crop's nutrient requirements. And what's important is that it's crop dependent, because different crops have different fertilizer recommendation. And above 100% is not necessarily nutritionally unsustainable, as long as we're not reaching concentration that could be harmful to the crop. And before we dive into the environmental and nutritional sustainability results, I just wanted to show you the mean concentration of NPK for the different years in the different aquifers. And we'll focus on the Western Negev concentrations and the Eastern Mount concentrations. We could see the big regional difference. They say the standard error is under 0.1 for all basins, nutrients, and years. And another important note is the Western Negev concentration used in this case, which are mostly from the Shaftan, are pre-soil aquifer treatment. So in fact, what the farmers are using are even lower concentrations than what we're going to see, than what we see here. Okay, so let's go into the results, and we'll start with environmental sustainability. And in this case, we focused only in fields that are in high sensitivity areas. So this is not all the fields, just ones that we know that are in the most sensitive areas. Again, what we see here on the left is for N, on the right is for P. The x-axis against the 5 years. The y-axis is the percentage of the total treated wastewater used in the basin. So if in the coastal basin we see an average is around 58 million cubic meters, and what percentage of that water is in each of the different categories. So what's in dark green means it's less than 50% of the standard, and what's dark purple means it's over 150% of the standard. For the N standard, like we said, 25, and the P is 5. So if we look at the N results, so on the one hand, we see differences in the different years. We also see difference in the different aquifers. For example, Eastern Mount, the majority of the water is above 150%, while in the coastal basin, we see that at least in most years, at least 50% is underneath the standard, and even when it's above the standards, it's only slightly above the standard. And for phosphorus, we see that on overall, more of the areas are beneath the standard. But again, this is very dependent on years, but also on the aquifer basins, like we see in the coastal basin, there was usually not a problem. But on the other hand, in the Sea of Galilee, in the Eastern Mount, we saw that almost all of the water, again, it's only in high sensitivity areas, was above the allowed standard for irrigation. So that was in the areas of high sensitivity, but it's also interesting to see what happens in the area of low sensitivity. And we show here the results for the two main basins, which have fields irrigating in low sensitivity areas, which is the Western Negev, which this is again mostly the Shafdan, and the Eastern Mount. And this is, I think, a very important graph that we see in the Western Negev, which is also the largest treated wastewater irrigation area. Almost all of the area is less than 50% of the standard. So what we're saying is the area with the lowest sensitivity is in many ways getting the highest quality water. And this also shows the difference between the areas. So while the Western Negev is doing very well, in the Eastern Mount, we see the quality is much lower. So before we were looking on the aquifer basin level, but we wanted to further increase the spatial resolution. And what we did here was a river basin surplus analysis. And basically what this means is for each one of these basins, we show the inputs minus the standard. So basically this means the inputs mean we took the concentration times the irrigation volume divided by the irrigated area. And for the standard, instead of the actual concentration, we took the environmental standard times the irrigation volume. So the difference between the inputs and the standards tells us, are we in a surplus or deficit compared to the standard, if we were irrigating it, of course, to the standard. So if we look at the nitrogen to the left, we see there's most of the areas is in a deficit, means the water is beneath the standard, the quality, but there's still some big basins like the Yarkon and the Kishon, which show a surplus above the above the standard, and also along the lower Jordan River and the upper Sea of Galilee, we see high levels of N. And in P, for phosphorus, we see that on the coastal areas, there's mostly not a problem. However, above the Kinneret, we do see a significant surplus of phosphorus. So to sum up what we're talking about in the environmental sustainability, we see a very large variability between years and regions. We see that overall N is less environmentally sustainable. However, in Sea of Galilee, P is a significant issue. And this is, we know it's also phosphorus is a problem there due to cyanobacteria blooms in the Kinneret. So there's this regional differences. And again, we saw that a significant percentage of high sensitive areas are receiving treated wastewater with environmentally unsustainable concentrations. And as I mentioned earlier, the low sensitivity areas like Western Galilee are receiving the highest quality or most environmentally sustainable treated wastewater. And this basically highlights the importance of matching the quality of the treated wastewater to the sensitivity of the area. And the analysis in a higher spatial resolution, like the river basin, can help identify hotspots for required treated wastewater infrastructure investments, like we saw, for example, in the Kinneret. Okay, next. Next, we're going to talk about the nutritional sustainability. So this is similar to what we saw before with environmental sustainability. Here we're comparing all sensitivity areas. On the left are results for the coastal basin. On the right are results for the Sea of Galilee basin and different crops. And we see in the parentheses on the top is the average area. And in the squared parentheses is the recommendation for irrigation. And here we see the percentage of the treated irrigated area above or below the required N. So like we see, what we see here is that for most crops, for nitrogen are below the required amount for the different crops, even though we see small differences between the crops. And the same thing is we see also in the Sea of Galilee, although here we see certain years where there was actually a levels that were above the required nitrogen. But I wanted also to show results for the Eastern Mountain Basin to show that this is not true for the entire country. So while in the coastal Sea of Galilee Basin, N levels were below the requirements, in the Eastern Mountain Basins, we see levels are higher for almost all the crops irrigated in this basin. Next, these are results for phosphorus and nutritional sustainability. So again, we see the same type of graph. And here we see that there's a much larger more crops that are get in the treated wastewater phosphorus that is above the required recommendation. And I should be clear here, we're talking about the concentrations in the treated wastewater before the farmer added any fertilizer. So this is only in the water he got from the reservoir. And so we see there's difference between the different crops, and there's also difference between the different basins. So if almond in the coastal basin received levels that are beneath 75% or less than what it needs, in the Sea of Galilee basins, we see almost all the almond got over 150% of what is required. Again, here we see the results for potassium, and I won't get into them, but again, we see here the same trend, which is first difference between crops and difference between years, and also difference between the different areas. Okay, so if we want to sum up the nutritional sustainability part, we see that it's determined by two factors. First of all, the nutrient content in the treated wastewater. Second, in the crop fertilization requirements. Like we said, there's a very large regional and annual variability. And this is again, I should say this again, that the above 100% of the crop requirement is not necessarily problematic as long as the crop is able to, is not harmed by these higher concentration, and as long as as it's not affecting the environmental sustainability. Sorry. And basically the bottom line is that maximizing nutritional sustainability requires maximum allowed treated wastewater nutrient content within allowed environmental sustainability threshold and beneath crop toxicity thresholds, which this basically says that less NPK concentrations are not necessarily better if we take into this consideration the nutritional sustainability aspect. And what we want to do is basically balance between the environmental and nutritional sustainability. And basically we're saying there's environmental and economic benefits in maximizing the nutritional sustainability. First of all, in that we don't have to spend energy in removing these nutrients from the treated wastewater, and also for the farmer, which he doesn't need to spend money on buying fertilizer. So if we'll summarize this second chapter, which basically I tell it from treated wastewater to nutrient water. And what this means is that we need to look at treated wastewater as a balance of water, nutrient, and salts. And optimizing the NPK levels needs to take into consideration both minimizing the environmental impact and maximizing the nutrient reuse for farmers. And this can and needs to be done on the management and irrigation basin scales, which means all the farmers receiving from a single reservoir or source. And this goes back to this importance of frequent monitoring and communicating it to the farmers so they can avoid unnecessary nutrient application. So we don't have a stage where a situation where they receive all the nutrient content their crop needs, but because they don't know the quality, just to be sure, they add additional nutrients. And another important understanding from these results is the importance of creating localized and regional environmental standards, which will allow us to maximize benefits and minimize pollution. So what we're saying, in areas that are not sensitive to high nutrient content, we want to allow farmers using higher levels of nutrient content to maximize the nutritional sustainability, again, without reaching levels that are harmful to crops. And basically what this also means that crops which have high nitrogen and phosphorus requirements are more recommended to be in low sensitivity areas and vice versa. And this will allow us to both maximize the nutrient sustainability while minimizing the leaching to the environment. So this sums up the second chapter. And now what I want to do is basically integrate our conclusions from these two different sections and ask ourselves what needs to be done to achieve or go towards sustainable treated wastewater irrigation. So again, I repeat, and I think this is one of the very important lessons, is the importance of the frequent monitoring and the transmitting to farmers and opening the data for research and analysis. The more eyes and the more data and the higher the resolution, the more in-depth and different conclusions you can reach from the data. And this is very important for the management of treated wastewater irrigation. Another aspect is the importance of the spatio-temporal analysis in increasing the resolution for hotspot identification, which by doing this analysis on smaller and smaller resolutions of area, this could help prioritize investment in treated wastewater infrastructure, which are very expensive. Another issue is the importance of defining the sensitivity zones and developing appropriate standards that will allow to maximize, like we said, both environmental and nutritional sustainability. So in areas which we know have potential in harming water resources, we will want to have low standards, while in areas which we know that there's no water resource that will be affected, we can allow much higher NPK concentrations. this going back to the desalination issue, and this is a thought that basically by distributing desalination, we can prioritize high salinity aquifer regions, which basically means if we know there are areas which have high salinity in aquifer, and if we distribute the desalinated for drinking water there, then the resulting treated wastewater will be a lot less, with a lot lower concentrations of salinity, and they could help reduce salinity in the groundwater. And the second part is distributing the treated wastewater according to quality and hydrological sensitivity. So if today the highest quality of treated wastewater is going to areas of low sensitivity, so we're thinking of a different approach. So take the best quality to the places that are most hydrologically sensitive. And like we said a few times, and I repeat it because this is, I think, a very important point, is that treated wastewater irrigation can be used as potential aquifer remediation service, and you can consider even promoting farmers to irrigate more than is needed, which can provide this service. So this is something that requires additional study and research. And we also require further analysis for problematic elements like magnesium and boron, and of course, additional pollutants that we did not discuss here. Okay, so I see I don't have time to talk about the interactive agri-atlas. I'll just go it really quick. Basically, this is a side project which I'll show to you in another time. Basically, what we did here is this: we integrated sources of data from different governmental agencies, and we created the spatial data set which maps the water use of agriculture in Israel. And what it allows is basically to analyze water use in Israel, check scenarios of changing crop types and water types and how that affects, and an interactive agri-atlas which allows users to compare areas and learn about different areas, about their water use and different crop use and additional information. Unfortunately, we don't have time for that. I just want to acknowledge our additional partners. First of all, the research was funded by the Chief Scientist Fund in the Ministry of Agriculture. Our partners were Professor Benchu, Dr. Yossi Tanai, Ariel Cohen and Matan Israeli from the National Parks Authority, and I want to also Asher Eisenkot and Barak Hagar. Additional data provided by Avi Aroni, also Israel Water Authority, National Parks Authority, Central Bureau of Statistics. And that's it. Thank you very much. And I'll be happy to answer any questions you have.
This is the time to unmute yourselves and ask questions.
No questions?
I think I have a question. So how can you talk about introducing treated wastewater into the aquifer without considering PPCPs and a lot of other elements that are really health issues and bacteria and stuff like that?
Okay. Obviously, what I'm saying is not let's do it tomorrow, but I'm specifically talking about the salinity aspect of it. And like we said, we need to see the whole picture and all the different pollutants which are in treated wastewater, and provide a complete solution for all these different elements before we consider using treated wastewater for introducing it to groundwater. But we have to remember that by the fact that we're irrigating today with treated wastewater, it's reaching the groundwater one way or another. So I mean, this is something that's happening, and if it's happening, so we want to prioritize. So basically, in areas which we know already have high salinity, by prioritizing treated wastewater with low salinity in these areas, we can get additional benefits. But of course, all these different contaminants need to be studied in depth and to see the implications on groundwater.
Okay, thanks. Otherwise, nice talk.
Thank
A
you.
lot of work.
Yeah, a lot of work, a lot of data.
I just want to add something to Shabtai's question, which I think is a really good point. And that's also to make a point that all this data was gathered from surveys, national surveys done by specific agencies, governmental agencies or others. So the fact that, what available is the parameters that we showed, should we add also, should there be also analysis of PPCPs, analysis of pesticide and insecticide added to this nationwide survey? Yes. The thing is that right now it's not done. So it's a good, or done partially. It's partially done. And a large, possibly a large scale and more intensive survey is may be called for.
So that should be part of one of the conclusions. Maybe you should take a little time to think which other things need to be included in light of your results that you can improve the aquifer.
Yeah. I'll mention that there's many different elements that are monitored that we did not include, but of course the temporal resolution goes down with the type of element. So obviously chloride and sodium are checked very frequently, but things like heavy metals and pesticides, which are much more expensive to test, are monitored in a much lower frequency. So it's also a question of cost, and but of course they need to check all the different contaminants at a certain resolution. So maybe once a year or once every 2 years, depending on the different contaminant.
I have a comment and a question.
Okay.
You say the irrigation with the treated wastewater that originate from desalination, desalinated seawater, may remediate groundwater salinity, and you show that the salinity of the Shafdan soil aquifer treatment, or the water in the Shafdan aquifer, are less saline than before. So this is a very misleading saying. You cannot take the Shafdan as a groundwater, and you cannot relate what happens below a field, an agricultural field that is irrigated with treated wastewater from which originate from desalinated seawater. So of course, the salinity is lesser than the older treated wastewater, but what goes under the root zone in the field will be more saline, still less saline than well, but more saline than the water in the aquifer. So that's a very misleading, and I'm telling you, the Shafdan, it's a percolation rate of 1 meter of water per year, whereas there's no evapotranspiration, and what goes in, what goes out. This is not a natural aquifer, and the aquifer under fields, the recharge rates are, let's say, 20, Shafdan 100, more than 100 meters per year, and the recharge under the field is maybe 20 centimeters a year. The salinities are much higher, and this is a misleading conclusion, and I think you should remove it. That's one thing. And then you speak about, on the second section of the lecture, you speak about the Eastern Mountain aquifer, and what treated wastewaters is the Nebi Musa wastewater treatment plant, which is that...
No, it's I'll explain that. That area includes also the Emek Israel Valley on the north. So a big part of it is actually those fields.
Okay. Okay. So, you know, if we don't know the water resources of Israel and show this to the world, we all know I don't know if we all, but we know the southern Jordan River, southern from the Kinneret, is a waste of all the northern part of the Jordan Valley. Yeah, it's the saline water from the Kinneret springs are going there, all the treated wastewater. The salinity of the southern Jordanian River is about 10 decisiemens per meter. So, like, this whole area is, let's say, deliberately, is how do I say, the garbage can of our water quality of our what we try to. So, and when you use also the treated wastewater plant, and it's non-comparable to what we have in the western of the country. These are extensive and not intensive treated wastewater plants. Also from the Bet Shean Valley, a lot of the treated wastewater, these are small treated wastewater plants and many. So for sure, this is nothing to compare to what we have in the West. So to show it on the same graph, when you show it to the international community, it's you have to put in some more other data to compare that. Yeah, that's the two comments I have.
Okay. So first of all, thank you for your comments. Yes, first of all, so of course, and I should have made it more clear that the Shafdan, we can't compare it directly to agricultural irrigation. It's not the same process, and that's true.
You can't compare it at all. There's
yeah,
no,
but what we're saying is, and this has to do, I think, also talk of Granot, your student showed about these places where they instead of irrigating only the crop requirement, so you could do irrigation in Be'odef, in
access.
And access and different. I mean, obviously this needs a lot more research, but this, and we're saying we're potential, and this doesn't mean that it's going to be the same dramatic effect that we see in the Shafdan, but in areas which suffer high salinity and were contaminated over years, we do think that there's potential, and obviously this has to be studied further in more detail before seeing how much, but the fact that the levels of the salinity of the treated wastewater are becoming lower than the freshwater concentrations does show that there's this potential that in over time, and especially as more and more desalination plants come in, this might be possible. Again, I agree that this is not, we need more data and more analysis to be able to say this for certain. Regarding your second comment, I agree that there's these different areas, and we focus mostly in comparing the coastal basin and the Sea of Galilee basin because of that. And the Eastern Mount, we didn't put as much attention because of that. And obviously there's different areas are treated differently, but this is also part of what we understand, is that we have to look at these things on a regional level. It's not enough to look just at the national picture. Each region and each area has its very specific characteristics, and this is part of what we're saying of like developing local standards of quality, which take into consideration also these hydrological differences, but also there's other differences in management. So I agree that the different areas need to be treated differently and need to be thought of differently. Okay, no more questions. Okay, thank you very much.
Thank you, Eliav, for your very nice talk.
Yeah, and if you have any questions, you're free to contact me on Irit by mail or by phone. I'll be happy to further discuss and hear comments, suggestions, and so forth.
Okay, thank you everyone for attending. See you next week.
Thank you.